Let's talk about the wind-driven coastal upwelling process, and it all starts with the surface Ekman. So if you have a wind stress, you have winds blowing over the ocean on timescales of several days and longer, a surface Ekman layer develops. Okay, and the surface layer, this layer develops under the influence of friction and the Coriolis force. So now the details are actually not important of this so-called Ekman spiral, which is shown here over next to my head. The Ekman spiral. What really matters is in the understanding of the ocean dynamics is only the net consequence. So first of all, the scale, thickness 50 meters. It's an estimate of the typical Ekman layer thickness. The net movement, okay, the net volume transport only depends on the wind stress, and you can calculate it. The net horizontal movement in the Ekman layer. The direction of the net residual direction is 90 degrees perpendicular to the wind direction, at right angle to the wind direction, to the right in the northern hemisphere, to the left in the southern hemisphere. So if you look into the wind direction, it's to the left in the southern hemisphere. Okay, so that's the starting point. This is what moves water induced by the wind. Okay, and important scales is the vertical extent, and also it takes several days for this layer to develop. Not too long, but also it doesn't happen within an instant of a second or so. All right. And there's a little photo here of Ekman. And if you wonder, how did he derive this theory? Okay. He actually derived this theory from the drift data of floating ice. Okay. And this was one of Nansen's polar expeditions, Fridtjof Nansen. And what they saw is that the ice drift is not into the direction of the wind. There is a systematic deflection between the direction of the ice and the wind direction, and always to the right. Okay, and then Ekman expanded this theory and applied it to the surface layers of the ocean. Okay, and he worked out the structure of the Ekman spiral. All right, that's the starting point. Yay!